Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. We are still in chapter 2, basic probabilities, and we are continuing with our concepts. Now, in the previous lectures, we talked about random experiments, we talked about the sample space, we talked about events, basic set operations like intersection, union, and complement. We talked about basic probability rules, including the axioms of probability, some basic probability formulas like the probability of the union. And in addition to this, we also talked about conditional probabilities, the multiplication rule, and the total probability rule. So what I just explained, what I just mentioned now summarizes pretty much the concepts that we have studied in the previous lectures slash in the previous videos. Now, today we would like to continue with our next concept here, which is called Bayes' theorem. So it's a theorem named after the person called Bayes. Bayes' theorem. Actually, it's one of the most important theorems in probability theory, and as you will notice, it has nice applications. Now, what is Bayes' theorem? I thought the best way to explain it is by using my own notes here, and the setup is pretty much the same as the setup that we used for the total probability rule derivation. So in the background, we have a random experiment that has sample space S. So this sample space is illustrated with the rectangle, the big rectangle, and we assume that the sample space has been divided into mutually exclusive events E1, E2, E3, and so on until EK. So these events are mutually exclusive. They don't intersect, as you see. There is no intersection between any two. In addition to this, they are also exhaustive. So they cover the whole sample space S. So the whole sample space is exhausted or covered by these events, E1, E2 until EK. Now, what is our target? Our target is to calculate probability of E1 given B, or to come up with a formula to calculate the probability of E1 given B, or E2 given B, or any one of them. It will be the same. So how can we get the probability of E1 given B? Knowing the opposite conditional probabilities. So basically, we assume that we know the probability of B given E1, so the opposite to this, B given E1 and the probability of B given E2 and so on until the probability of B given EK are all known. And actually, these are precisely the probabilities that we used in the total probability rule last time. You can see the total probability rule here in the denominator. So the probability of B is the probability of B given E1 times the probability of E1 plus the probability of B given E2 times the probability of E2 plus and so on until the probability of B given EK times the probability of EK. This was the total probability rule. So we were able to express the probability for B, the probability of B, knowing these conditional probabilities B given E1, B given E2, and so on. So the probability of B given E1 and B given E2 and so on until B given EK are all known. And knowing those, we are interested in calculating the opposite conditional probability. In other words, we would like to infer the probability of E1 given B from the opposite conditional probabilities. So how can we do that? Actually, the proof is quite simple. So let me start with what we want here. We want the probability of E1 given B. So it's a conditional probability. What was the rule or the formula for conditional probability? This straightforward formula is the probability of E1 intersection B divided by the probability of B. So an intersection probability divided by the marginal probability of B, because we have given here B. So probability of E1 intersection B divided by the probability of B. So this formula gives us what we want. However, to reach the actual formula that will be useful to us, we would like to replace each of the numerator and the denominator by their equivalent forms. So what is an equivalent form of the probability of E1 intersection B? Using the multiplication rule, the probability of E1 intersection B is the probability of B given E1 times the probability of E1. So this is the multiplication rule. We know that we have B given E1 here, given E1 times the probability of E1. That gives us the probability of B intersection E1, the multiplication rule. So the numerator becomes the probability of B intersection E1 times the probability of E1. What about the denominator, the probability of B? Probability of B looks like the total probability rule. We can replace the probability of B by this sum. Probability of B given E1 times PE1 plus probability of B given E2 times PE2 and so on. So as you notice here, the probability of E1 given B is a fraction. In the numerator, we have the probability of B given E1 times the probability of E1, and in the denominator we have a total probability rule. Now this formula has a very nice structure. So in the denominator we have the total probability rule. We have all terms here summed up. We have the summation of all the terms. And in the numerator we have the first term here. So the first term appears in the numerator. If we extend the idea, I think it's very easy for you to imagine that if we wanted the probability of E2 given B, we could have done exactly the same development. However, the result is the following. If we wanted the probability of E2 given B, the denominator would be exactly the same, the total probability rule, but in the numerator, we would have the second term, the probability of B given E2 times the probability of E2. What you see here is called the Bayes formula. This is what you see here. Bayes formula, the probability of E1 given B is equal to the probability of B given E1 times the probability of E1 divided by the probability of B given E1 times PE1 plus all the other terms. So as you notice, if this is unknown here, if the left is unknown, then the right is known, and this is what we need to substitute with. So what do we know? We know all conditional probabilities B given E1, B given E2, B given E3, and so on. And we also know the probabilities for E1 and E2 themselves. Using this information, we can infer the probability of E1 given B. Now, this may look really dry for you, and you might be confused. Why are we using that? Now, I think the best thing that we could do is to look at this example, which looks pretty much like a practical example. So it does not only serve as a numeric example, but also as a motivation for this study. Why do we use Bayes formula? What do we use Bayes formula for? So let's look at this example here. The example says a printer manufacturer, like a factory that manufactures printers, realizes that printer failures are associated with three types of problems. So they have noticed that if a printer fails, this is due to one of three types of problems, either a hardware problem, a software problem, or another type of problem. So we have three problems: hardware, software, and other. Also, from the previous history, from our previous knowledge, it is given to us that these problems occur with probabilities 0.1, 0.6, and 0.3. So what are these probabilities again? These are the probabilities of hardware and software and other. So what we are given here is the probability of a hardware problem is equal to 0.1. The probability of a software problem is 0.6. The probability of another problem is 0.3. So this is what we can write down using the notation, but the actual problem as it is given is just this text. So the probability of hardware, software, and other. In addition to this, we have some other probabilities given, as you see, 0.9, 0.2, and 0.5. I think you may expect that these are conditional probabilities, and that's true. So let me read the sentence. The probability of a printer failure given a hardware problem. So the probability that the printer fails given that we know it's a hardware problem is 0.9. So if I have a printer and I know that there is a hardware problem, the probability that it will fail is 0.9. So the probability of failing given hardware problem is 0.9. The probability of failing given a software problem is 0.2. Failing given software is 0.2. The probability of failing given any other problem is 0.5. So the probability of failing given any other problem is 0.5. So these are the 6 givens here. We have 3 marginal probabilities, which represent the types of problems, and 3 conditional probabilities, which is the probability of failure given any one of these problems. This is what is given. Now, what is the problem here? You choose a printer at random. Before I read this question, by the way, if you see a problem like this in which something like that is given, there are only 2 questions or only 2 types of questions that we can ask. Either a total probability rule or problem that is using Bayes formula. So either I ask you what is the probability that any printer fails, given what we have here. What is the probability that any printer fails regardless of the problem? To solve that, it would be the total probability rule, as we have talked about last time. However, here we have a Bayes formula question. So let's read the question first. You choose a printer at random. So let's say I close my eyes, I go to this room full of printers, I choose one at random, and now I test it and I find it doesn't print. So I find it has a failure. You choose a printer at random and find it has a failure. So this is something that we know. We know already that it has a failure. The question is, what is the probability that this failure is due to a hardware problem? So what are we asking for? Are we asking about the probability of having a hardware problem, or are we asking about the probability of failing? Basically, what we're asking for is what is the probability of failing given that the printer has a hardware problem. We are asking about the probability of hardware problem. Sorry, I think I made a mistake. You choose a printer at random and find it has failed. So what we know is that the printer has failed. The question is, what is the probability that it is a hardware problem? In other words, we need the probability that we have a hardware problem given that we know the problem, given that we know the printer has failed. So what we want is a conditional probability, which is the opposite to this one. Again, let's try to make sense out of it. You choose a printer at random and you find that it has failed. So we know the printer has failed. So given that the printer has failed, what is the probability of having a hardware problem? So what we want is the probability of a hardware problem given that the printer has failed. So as you notice, this is not given here. What we have given is basically a bunch of marginal probabilities, hardware, software, and other, and we have some conditional probabilities, failing given hardware, failing given software, failing given another type of problem. But this requirement, this question here, is not given. What is the probability that we have a hardware problem in the printer given that it has failed? Before we solve the problem, as you notice, we apply Bayes formula. We can also apply the tree. I will comment on that. However, let me just comment on the importance of this. Now, these conditional probabilities are known, and these could be known from the previous history. So in that company, we know that if a printer has a hardware problem, it fails with probability 0.9. So 90% of those printers that have a hardware problems fail. 20% of printers that have a software problem fail. 50% of printers that have another type of problem fail. So this could be known from the previous history, from the previous data. Now we have a particular printer. I picked a printer at random and I found it has failed, but I don't know what problem caused this failure. So I'm interested in calculating what is the probability that the problem is a hardware problem, because I don't see the problem yet. I don't know the problem yet. So I would like to calculate the probability that the problem is a hardware problem given that we know the printer has failed. Why is this important? Maybe if I calculate this probability, I would have some insight to what is the most likely reason of this failure. Maybe I can decide to which department I can send the printer, hardware or software, or another department, so that they can start checking the printer and start fixing it. So this is basically the motivation behind Bayes' theorem. It helps us infer a conditional probability from the opposite conditional probabilities. These opposite conditional probabilities might be known from previous history, from previous knowledge, from previous data, but this conditional probability might represent something new, and it would be important to us to calculate this probability. Now let me go back to the question as a numeric question. We need to calculate the probability of having a hardware problem given that we have failed. Since it's a conditional probability and we know the opposite ones, so this really calls for applying Bayes formula. In Bayes formula, we have here hardware given failure. So on top we have probability of failure given hardware times the probability of hardware, and in the denominator we have a total probability of failing given hardware times probability of hardware, plus probability of failing given software times probability of software, plus probability of failing given other times the probability of other. So we just substitute here and we do 0.9 times 0.1 divided by the sum here. So the answer is 0.9 times 0.1 divided by 0.9 times 0.1 plus 0.2 times 0.6 plus 0.5 times 0.3 here. So this is what we have. This is a typo here. You see that this is a typo, and the last term is 0.5 times 0.3. 0.5 times 0.3. Okay, so if you do the calculation, you will find that the answer is 0.25. So this is the answer. 25% is the probability that the problem is a hardware problem, given that we know it has failed. Likewise, we could have calculated the probability of a software problem given that the printer has failed. What would change here in the denominator? It's still the total probability rule. We still have all the terms, but in the numerator, we would have the second term, 0.2 times 0.6. You can do it as an exercise. Finally, how could we have solved this problem using a tree diagram? And this simplifies, it allows us just to write an equation with numbers without having to think about the symbols too much. So we start with the following here. These are the marginal probabilities, hardware, software, other, and this is what we start with. So if we have a printer, we could have a hardware problem, a software problem, or another type of problem. On the branches, we have probability 0.1, 0.6, and 0.3, 0.1, 0.6, and 0.3. Now, given that it's a hardware problem, it might fail or not. Since we're talking about failure here, so it means that we have only two possibilities, failing or not failing. So given a hardware problem, the probability of failing is 0.9 here. The probability of failing is 0.9. Given a software problem in the second branch, the probability of failing is 0.2. Given any other type of problem, the probability of failing in the second branch is 0.5. So these numbers, 0.9, 0.2, and 0.5, as we are used to the tree diagram concept, these are conditional probabilities. The probability of failing, given that we have a hardware problem, because this branch is coming out of hardware. Now, what about the red numbers? Again, these are the other numbers that are not given here explicitly, but they are implied. So if 0.9 is the probability of failing given hardware, then 0.1 is the probability of not failing given hardware, 1 minus 0.9. Likewise, 1 minus 0.2 is 0.8, and 1 minus 0.5 is 0.5. We are not using these numbers in this problem. However, if we just change the problem slightly, we could have used them from the beginning. Like, for example, the problem changes into you choose a printer at random and find it has not failed. Find it has not failed. It's working fine. What is the probability that the printer still has a hardware problem? So this is something that we may want to calculate. What is the probability of a hardware problem given that it has not failed? So think about that, but let's go to our original question. We need to calculate the probability of hardware problem given that it has failed. So hardware given failed. How can we use the tree without having to think about the formula explicitly? So hardware and fail, 0.1 times 0.9. This is hardware and fail, and this is what we have on top in the numerator. In the denominator, it's the total probability rule. We add all the branches that lead to fail. So this is fail, and this is fail, and this is also fail. So divided by 0.1 times 0.9 plus 0.6 times 0.2 plus 0.3 times 0.5. Again, we have the same typo here. This is 0.3 times 0.5. If you do the calculation, it's pretty much the same as what we have here. But if we draw the tree, we were able to write the numbers directly without having to write the formula using symbols. And this finishes the chapter. Basically, we have a small concept called random variables, which is an introduction to the next chapter, but I prefer to talk about that in chapter 3 itself. So see you in the next lecture in chapter 3, inshallah. Thank you so much. Assalamu alaikum wa rahmatullah.